we're looking at the remaining two properties of conductor regarding to electrostatic phenomena. So now, perpendicular electrical field lines. So if this is a conductor, surface of a conductor, remember the conductors can be in any shape, right? Any weird shape possible. So the point here is that the field lines are always perpendicular to the surface. They're always perpendicular to the surface. So how is that we are going to prove it? Well, say we'll look at a scenario where it is non-perpendicular, say at an angle. So let's consider an electrical field non-perpendicular to the surface. Thus, we can resolve it, right? It will have both parallel and perpendicular component. So let me redo this diagram. So what I'm trying to tell over here is, say we have a non-perpendicular component or electrical field line on a electrostatic. Remember, this has to be electrostatic, right? So we can resolve this to parallel to the surface, perpendicular to the surface. Is it not? So we're going to start off with the electrical field lines are always opposite to the rate of change of velocity with respect to distance. So now on resolving, so what do we end up with? Minus dv perpendicular and d parallel and perpendicular. My bad, parallel and perpendicular. But a conducting surface has a constant potential when in electrostatic, when at electrostatic. The grammar is not exactly right. Let me think over it. Okay, guys, this is a conducting surface has a constant potential when it's at electrostatic equilibrium. Now it's right. Okay, my handwriting is not. Okay, now also it's not that great, but yeah, let me continue. This implies V parallel in our case is equal to a constant, and therefore, no space over there, therefore this component will be equal to 0 and E will be equal to only the perpendicular part. It's always perpendicular to the surface. Agree? So the rate of change of voltage with respect to distance happens only in the perpendicular component and not anything to do with parallel component. Okay, so that's how you can prove that. Now, next is to do with your surface. It's commonsensical again. More the surface charge or more the charge on the surface, more the field lines that will be coming out. As simple as that. So let's consider a conductor. Now, we will consider a Gaussian surface, right, which is closing a small section of the conductor. So this area, say that is A, and so this too will be A. So this is our conductor. And that's our Gaussian surface. right? Okay. Why is that? What is that we are trying to make use of it? If you remember Gaussian surface, what does it tell? Actually, Gaussian surface is an imaginary sphere, but where is that we are using that? Yes, in the concept of flux, right? So we have the density Q by epsilon naught, right? Which is, agree? Sorry, the flux is equal to Q by epsilon naught. This is as per by Gauss's theorem. So what does it tell? You look at the number of field lines that is coming out. It has to be equal to the charge that it occupies or it has within that surface divided by a constant. So here your rho is your surface charge density. I think it is sigma, supposed to be sigma. Rho is that, yeah, sigma. This is sigma. Surface charge density. Right, guess. And A is area. Area of the top, I guess. Area, let it be that. But we also know what the very definition of, as per the definition of your flux over here, what do we have? We have E into A, right? Flux density in some manner into the area. So from 1 into what can we tell? So from 1 into, we have EA rho A by epsilon naught. E and A will get cancelled. So E is proportional to the density. That is, if I increase this too increases, right? And that's your proof. Hence proved. Okay, so let's look into what we just studied. We understood two things, that when it comes to a conductor, when it's at electrostatic equilibrium, we have the field lines to be always perpendicular to the surface. We have seen this in many scenarios. Again, we are repeating it, but the way we are proving it, it's different. Of course, you can just write up, explain it also, but for me, this is simpler. Maths is simpler for me. So we are using proof by contradiction, wherein we are considering a non-perpendicular electrical field and then resolving it. So on resolving, we end up with this. But we know that the conducting surface has a constant potential when it's at electrostatic equilibrium. And so this is constant, so the derivative of that is 0, and so we end up with only perpendicular component. Now, electrical field on a surface is given by the density it has. And the proof goes like this. We know that flux has two different expressions. One is as per the definition and another as per your Gauss's theorem. When we equate it, area gets cancelled, and we can see that E is proportional to, yes, your sigma, the surface charge density, and we have proved it.